All right. Welcome back to the final uh, session of set of videos, one video recording for cluster analysis and cluster analysis heat maps for data science methods for digital learning. So in this last video, I'm going to talk through this recent paper that I had with a few colleagues here at Teachers College at Columbia University. That's published in the high school journal towards hierarchical cluster analysis heat maps as visual data analysis of entire student cohort longitudinal trajectories and outcomes from grade 9 through college. Now, this is going to mirror the 2010 paper a little bit, but one of the reasons why I want to talk about this paper is that A, it's more recent. B, it also includes, as you can see on this slide, the open access R code tutorial. So while the data set is restricted, but it can be obtained from the U.S. Department of Education because it's every single grade and every single subject for students from a nationally generalizable sample of students in high school and college in the United States. We also included not only an R Shiny application where you can upload an Excel file and it'll make a cluster analysis heat map for you. And I'll show an example of a paper that recently came out that did exactly that. But then if you want to run the code, the R Shiny app code locally, like in an encrypted environment, because you might have restricted data, you can also, that code is available open access as well. And then we've got our markdown that walks you through how to do cluster analysis heat maps in R using a package called Complex Heat Map. And so in this final video, I'll walk through the paper and then walk through the tutorial. And then you should be able to do it yourself, which is kind of the point. So in this paper, our original motivation for the paper was that there's a growing body of research on early warning systems and early warning indicators for use in data-driven decision-making and evidence-based practice. I've done some of this work. So a lot of people are calling for early warning indicators. Some of the most predictive variables are student grades and non-cumulative GPA. Yet recent randomized controlled experiments using early warning systems and early warning indicator dashboards have shown little relationship with overall student outcomes. Most of these are in the United States, but if you give school districts a dashboard with early warning systems in it and in early warning indicators, you don't get much of a change in the randomized controlled experiments. The majority of early warning system and indicator research and practice focuses on individual variables and student at-risk scores. So like I was talking about in the last video, the focus on single indicators and averages fails to see the individual student in the data and describe the longitudinal patterns of how students have performed in the system provided them to date. So our idea here in this paper, our supposition here is that these findings suggest that perhaps current data summary practices that focus on bar graphs, line plots, and summary averages across schools could be augmented and complemented through adding additional tools to the education data analyst's toolbox that provide additional views into the life course of students throughout their time in school. So we introduce this idea and move forward on this idea of visual data analytics using hierarchical cluster analysis heat maps. So visual data analytics is, quote, designed to help expose patterns, trends, and exceptions in very large, heterogeneous, and dynamic data sets collected from complex systems. And this is within the exploratory data analysis, the EDA research domain, which has been going on for 50 years or more, in which exploratory data analysis functions to address the broad question of what's going on here, with an emphasis on graphic representation of data, in which the goal of EDA is to discover patterns in data. So I hope you can now see through all these videos in this section of the course that I'm going to make the argument that hierarchical cluster analysis heat maps are perhaps one way to go about describing these patterns. And we're going to look at longitudinal student grades as a descriptive pattern analytics. And as we've talked about in this class, hierarchical cluster analysis heat maps are used extensively in big data, data science, and bioinformatics fields. So the research question for this paper, to what extent are student grading patterns from grade 9 through college identified through hierarchical cluster analysis heat maps using a national sample of over 14,000 students? So I also want to show you this paper because I've got 14,000 rows in a cluster analysis heat map and show you that it's possible to be able to do this and still come to some interesting conclusions. So the idea for this study is that we are using the education longitudinal study of 2002, high school and post-secondary transcript study. So the National Center for Education Statistics collected the entire transcripts for all students for a nationally generalizable sample of a little over 14,000 students across 450 individual subject grades from grade 9 through college, which represents almost a little over 6.5 million individual course grades, which we then z-score. And so, and you can think about the ELS 2002 data set. The students were in 10th grade in 2002, and then they were followed and surveyed and their data collected over many years, including 2006, 2008, so 2006 when they should have graduated high school, 2008, and then there's a follow-up that comes as well in 2012, where they look at them 10 years later and also collected their entire college transcripts. Well, and so the NCES had every single grade in every single course in high school and college. And what was really interesting as well is that the NCES standardized all the grades and all the courses to 54 standardized subjects in high school using the classification of secondary school courses, CSSC, and then college as well using the college course map for every year. So they have a standardized set of courses. So here you can see in the paper, we talk through in this figure how we processed the data and cleaned it because we had to delete a few people based on missing data. But overall, we were able to include a lot of students, almost 15,000 across 450 subject grade columns. That includes every subject in high school and every subject taken. And so we used hierarchical cluster analysis heat maps with uncentered correlation and average linkage. And so these are the 54 standardized subjects. And as you've seen before, we'll order things actually here from using the CSSC course numbers, but they focus on putting courses into these different groups. So, and these subject specific codes. But what's interesting is the NCES got the actual course catalogs from every single one of these high schools. So it's really comprehensive. They've got like every subject you can think of, and they put every course in it. And so again, here, time will be on the x-axis, and the cluster tree and 14,000 rows of students will be on the y-axis. So every subject will be represented by a column, z-scored, for their grades, students by rows. Blue is a low grade z-scored, gray is going to be the average, and red will be high grades. White will be no data, so they did not take that class. And then we've got high school grades 9, 10, 11, and 12, and then 2006 as a dual enrollment year, and then 2007, 8, 9, 10 in college. And then the covariates, the dichotomous outcomes and distal outcomes, which we looked at many, will be but they were outside of the cluster analysis. Those will be on the far. So this is the cluster analysis heat map, and you've got the cluster tree on the far left, as well as the annotations on the far right. And again, red is high grades, blue is low grades. And so our first main finding is that we replicated the 2010 paper in that there's generally two main clusters, a high grade cluster and a low grading cluster. Number two, as far as overall findings, you can see that past grades performance generally predicts future performance. If you look left or right, so in the bottom cluster, the students in high school usually get high grades. If you get high grades, you usually get high grades in all subjects throughout. And then there is in the upper cluster, cluster 2, there is subcluster C that I'm going to talk about in a minute. But especially for subcluster D, the students get low grades starting in ninth grade and continue to get low grades throughout. Point number three, there are few, if any, columns that stand out. If a student does well or poorly in one subject, their grades are similar in all subjects. We really find that there are no gateway classes. There's really not really students who like do great in art but fail math. If you do poorly in one class, you're going to do poorly in the other classes. And our other big finding is that cluster D is identifiable at grade 9. And these students, as you can see, they're blue. So they're low grades at the beginning of grade 9. This is easily identified, and the students continue to get low grades. There's no big cluster of low graded students who then rise over time. And so these students struggled from the beginning and continue to struggle. And then looking at the covariates, these annotations, we looked at a lot of outcomes from high school dropout. So you can see the dropouts are here in the upper cluster, just like in the 2010 paper, whether or not they took the ACT, SAT, all the way out to STEM occupation. Did they get a STEM degree at age 20? Or did they get a STEM degree? And they're by age 26, are they in a STEM occupation? As well as many demographics, and then their overall high school GPA at the very end as a heat map itself. But if we focus in on specific subclusters, so this is cluster 1A. You can see these students basically do well throughout their entire time. There's a few courses here and there that a few students struggle in as they move through. They're indicated by the blues. But otherwise, red dots means high grades in those courses. White means they didn't take those courses. There's a lot of courses that students don't take that have a subject code. And almost all of them graduate and take the ACT, SAT, so college entrance exams. This is in comparison to cluster 2D, which are the low graded students. From the beginning of ninth grade throughout, they're getting low grades. Some of them end up going to college, but they struggle. This is where the dropouts are, and a lot fewer students take the SAT, ACT. And so there's other subclusters like cluster C, I think is quite interesting. They kind of struggle. They're in the middle in high school, and then you can see when there's a group of them that when they slam into college, it's really hard. It's blue, and it's like, boof, and then they're gone. What I think is really interesting about this kind of analysis, yet again, is there's 450 columns of data, 14,000 students, every single data point is displayed, but patterned in a way that we can see all the patterns and make inferences ourselves as the reader and come to our own conclusions. And then you can then interrogate the author, who happens to be me, but interrogate the author's opinions, in the discussion, but don't have to trust them. Everything's here. There's no p-values. There's nothing hidden. Everything is right there in front of you. And so you can imagine, if you've got clickstream data, log file data, tens of thousands of rows across thousands of columns, cluster analysis heat map will render, and you can make really interesting inferences and really see interesting data patterns. And so as we talk about in the paper, we have the open access R code it just runs in our Shiny environment. It's also copy pastable. So it's a low code, no code. You can upload your Excel files. If you put an asterisk in front of a variable label in your Excel file, it'll treat it automatically as an annotation. So that's how you see dropout took ACT here. This is the data from the 2010 paper uploaded to the Shiny app in an Excel file, and it replicates quite nicely. And so, if you don't want to code, here it is. I will tell you, we use the free version of Shiny. And so I think we only get like 20 hours of use every month total. So as soon as those 20 hours total are used up, you'll get an error message. So if you get an error message, it doesn't mean it's down. It's just like the free version. We don't have a whole lot of money to pay for a website for the Shiny app to run. And so it's kind of throttled. But people are using it for research papers. Here's a recent paper from 2022 in which data from the OECD TALIS data set is compared using the Shiny app for cluster analysis heat map. in which then they look at cultural differences in how school leaders and teachers respond to the TALIS survey from the OECD. And so conclusions and contributions for this paper. Hierarchical cluster analysis heat maps are useful means to describe the patterns of individual students, and look at see their data patterns and visualize what we call in this paper the social curricular ecosystem. The NCESL's 2002 longitudinal grade patterns show that early grade patterns can be identified at grade 9 and are predictive of overall high school and post-secondary outcomes. For early warning systems, visual data analytics offer an additional exploratory data analysis tool for data analysts and education data scientists to see the individual within the larger patterns of the system. And we're happy to share the R code in a quick tutorial, which I'm going to go over right now. So in the paper and on these slides, we link to the open access R tutorial. It's published under a Creative Commons license, so feel free to mash it up and take it and do whatever you want, as long as you give it, cite us, do whatever you want with it. And one of the things that I really wanted to work on and show with this markdown is that the complex heat map package in R by GU is incredible. It can do amazing things. I'm going to show just the very beginning here. But I hope that it opens the door so you can see how to really expand your use and thinking about cluster analysis overall and how to visualize your data with a cluster analysis heat map. I'm going to walk through data cleaning, plotting the HCA heat maps using the defaults, then show you how to do uncentered correlation and average linkage, and how to add annotations and covariates and distals that are outside of the cluster. So just a quick note, this whole uncentered correlation piece, you need a package called HOPAC. You have to install using DevTools and the bioconductor packages. And so the way to get to be able to do uncentered correlation, I talk about it in the markdown, but I wanted to note it here. This is the website to get HOPAC from, HOPACH. But this will do the cosine angle for the uncentered correlation calculations. It's not available on CRAN, so you just got to install it using this code right from Bioconductor. So, and the reason that it's on Bioconductor and not on CRAN, I don't know. You'd have to talk to the people who made the package, but the package is used a lot in bioinformatics. And so that's why it's on Bioconductor. So let's get into the markdown. So I encourage you to follow along. You can just download the markdown. It's open access. Follow along. I'd encourage you to then copy paste the code right into R so that you can generate and have a hierarchical cluster analysis heat map when you're all done. So this is the top of the file. It talks through, a couple citations, and then to install a complex heat map as well as HOPAC, and you need a couple other packages. So then the data set that I'm going to use here to show the tutorial is the MT-CARS data set that's inside R. So MT-CARS is the motor trend car data from 1973, I think, in which there were some really great cars and some really terrible cars. So you've got everything from the giant car, the Cadillac Fleetwood, that was just a giant gas guzzler. This in the mid-1970s in the United States was just like, yeah, terrible cars, but then amazing cars. So the Datsun 710 was just a hilariously bad car. The Maserati Bora is just a absolutely fabulous car. The Chrysler Imperial was like a boat basically on the road. It's gigantic. And the Ferrari Dino is just like a collector's car. It's absolutely amazing. And so MT-CARS is right in R right now. All you got to do is open it up. And if you just do like the code right here, head MT-CARS, you'll see that you've got all this data from Motor Trend from 1973 on each of these cars. So we have variables like miles per gallon, the number of cylinders, displacement, horsepower, draft, weight. QSEC is how fast from, how many seconds from, I believe, 0 to 60. VS is how the engine is oriented. AM, I'll get to in a minute. Number of gears, and it's down here. Carb is. Oh, I forget what carb is. The VS is V-shaped or straight, and AM is automatic or manual. So we're only going to use the first 7 columns. So let's make data empty cars. 1, 2, 3, 4, 5, 6, 7. So we're only going to use this data to start with. So first, if we want to do a cluster analysis heat map because we want to see the cluster analysis. Let's pattern all this data to see what cars are gas guzzlers versus which ones are more fuel efficient. Like, how do they go together from this time period? So first, because the data is weird, I mean, we'll go back up. I mean, if we didn't rescale and z-score this, so the cluster analysis will just see the numbers in their original metrics. So the biggest numbers will pull all the data towards it. So displacement and horsepower are 2 of the biggest numbers. So anything else won't really matter if we didn't z-score. So the first thing we do is we z-score. So just all you got to do in ours, scale the data, and then see now everything's on the same unit measure on standard deviation units, with 0 being the average. Okay, our first heat map with complex heat map. So complex heat map is great. Gu did just an absolutely fabulous job. His book online is open access. You can just go right to it. I just search for complex heat map. We also link to it in the paper. One big thing to note is that in your code, H in heat map must be capitalized. If you don't capitalize the H in heat map, you'll call a different heat map package if you have a lowercase h. So if you're getting weird errors or it's not doing what you want, check to make sure that you have a capital H for when you're calling your function in heat map. And that means you're calling complex heat map. Why is it this way? I did not code the package, so you would have to ask the package author. This is the way it is, and so there you go. To be able to do our first cluster analysis and heat map with the MT cars data, here we're just going to not even cluster. We're just going to show a heat map of the data and what the data frame actually looks like with no clustering to begin with. So actually, we have to turn everything off. And so the code's really straightforward. So here, you just have a heat map of the data, the z-score data, and all of the different colors. So then if we want to do the default clustering on the rows, which is going to be Euclidean. So, and then default is going to be complex. So this is the code. It's pretty straightforward. And now you can see that we've got multiple types of cars that you probably would, most of them you'd put together are clustering together. So like the really big cars with terrible gas mileage, miles per gallon are really low. They're all up here together. You've got some of the hot rods are here together but also some of the more like the Toyota Corolla, the fuel efficient car is coming in. But we can do better. Let's see. So these are the defaults. Let's also do both the rows and the columns. So now you start to get the classic checkerboard pattern, which is really nice when you are clustering both the rows and the columns. And now we see that things like QSEC, MPG, and draft, they all cluster together. It's kind of like a little like factor analysis, maybe, where your features are now clustered, and then weight, horsepower, number of cylinders, and displacement, they all go together. But we didn't change the order of the rows, so here they're the same. So now let's calculate uncentered correlation and cluster with average linkage instead. And so you have to have a little function to use the cosine angle from the Hopak package to be able to do this. And then all you got to do is use that function on your data set and then just call AVE for average linkage, and you're good. And it's the same code as above. And now you get really tight clusters, which is really nice. And on top of that, so we've got first, the gas guzzlers are all right where they were supposed to be. And then you've got the Ferrari dyno and the Mazda RX-4. These are, and really the Merc. These are more the hot rod style cars. The and they go together. You got the sure, you got the Toyota Corolla, but the Datsun, they go together, which is nice. Should they be near the Porsche? Well, we got the data that we got. But what's really nice is you can see the splits and how nicely the cluster tree really shows these different differences. And really, the Ferrari dyno is really super different than everybody else up here. As is the in this lower cluster, you can see how different the Hornet and the Valent are than everybody else and all the other cars as well. And then if you want to add annotations, all you got to do is use this kind of code, and you can bring in like the transmission, the manual automatic, the cylinder configuration, whether or not it's inline or V-shaped. And you can see that like the hot rods have the manual transmissions and an inline cylinder configuration much more often. And then but we didn't use these variables in the actual clustering at all. And that's the tutorial. Everything's there. You should be able to replicate it, and then be able to plug in your own data after that to begin doing deeper analysis. Now, just as we end here on this final video of the clustering and cluster analysis heat maps, I just want to talk up the complex heat map package and reference guide just a little bit more. Everything's here that you could ever need when it comes to cluster analysis in R with heat maps as well. And the heat maps are very, very extensible with all kinds of interesting annotations. I really am excited to see where people who take this course can really take cluster analysis heat maps, especially using such fabulous resources as these open access resources that are online, where you can just copy paste the code and just get it working right away in your own R Studio implementation or R Markdown. And so that's the end of my videos. Thanks so much for participating in this part of the class. I hope that you got something out of this idea of being able to use visual data analytics and cluster analysis heat maps across the kinds of data that you can use as for your rows and your columns when it comes to thinking about being more serious about these descriptive analytics and visual data analytics, and really looking at these large-scale correlational methods, such as cluster analysis and cluster analysis heat maps, so that we can really begin to look at the patterns in our data, but also see the individuals and the individual information throughout these kinds of data visualizations like we can do with cluster analysis. So thanks so much, and I hope you are enjoying the sets of courses. And if you ever see me around, say hi. I'd love to talk to people. So thanks so much.